All right, let's talk about generative AI. And I promise, this is going to be way bigger than just AI makes pretty pictures. We're digging into a really fundamental shift here. We're moving from AI just creating static pixels on a screen to it actually simulating the tiny dynamic particles that make up our physical world. So yeah, let's get right into it.
This one sentence. This is the key to everything we're going to talk about. For years, we've seen generative AI as this brilliant artist, an expert at mimicking the patterns it sees in data. But what's happening now is a huge pivot. AI is becoming less of an artist and way more of an engineer, learning to simulate the processes that govern how reality actually works.
And that is the million-dollar question, isn't it? This one shift changes pretty much everything, from how we design cars and discover medicines to, honestly, the very nature of truth itself. So let's trace this incredible journey, and we'll start at the beginning, with the foundation that made it all possible.
Okay, so our story kicks off in what we can call the age of pixels. This was the era of the first big breakthrough generative models. And what's so fascinating here is that their limitations, their actual flaws, were the very things that forced the entire field to evolve and get smarter.
It was this classic problem, solution, new problem kind of thing, First up, we had these things called VAEs, and they were fine. They were stable, easy to train, but their fatal flaw? They made blurry, fuzzy images because they were basically just averaging out pixels. Then, boom, GANs come along. And this was a brilliant idea. You have two AIs fighting each other, a generator and a critic, and this competition forced them to create these incredibly sharp images. But, and there's always a but, right? GANs were a nightmare to train, super unstable. And they had this weird problem called mode collapse, where they just get stuck making the same couple of images over and over again. It was this exact tension, this back and forth, that really pushed the whole field forward into the next big leap.
So the next phase was all about breaking free from that flat 2D image. AI had to start learning about time, motion, and the third dimension. Now this was a super important kind of intermediate step where AI began to learn what physics looks like, even if it didn't really get how it works yet.
And this, of course, presented a massive challenge. I mean, think about it. We have trillions of images online, but there just weren't these huge high-quality data sets for things like 3D models or audio or video. So developers had to get really clever. They couldn't just throw more data at the problem. They had to find a shortcut.
And this is that brilliant solution. They found what you could call a common substrate. So, to generate audio, models like AudioLM learned to turn sound waves into text-like tokens, basically treating audio like a language problem. To generate 3D objects, they were judged on how realistic they looked from every possible 2D angle. And for deepfakes, faces were broken down into an abstract code of features, like pose and expression, that could just be swapped around. They were basically compiling harder problems down into simpler ones they'd already cracked. Right, so the crucial point here is that even a model as mind-blowing as Sora is still at its core an expert mimic. It's trained on countless videos, so it has learned this implicit, appearance-based model of physics. It knows what a wave breaking on a shore looks like, but it has no clue about the equations of fluid dynamics. It's really the absolute peak of imitation, which sets the stage perfectly for the next paradigm. And that brings us to the climax of our story, the huge leap from pixels to particles. This is the moment where AI stops just mimicking the appearance of reality and starts to understand the laws that actually govern it. We are moving from what's visually plausible to what is physically provable.
Now, what I love about this slide is how clearly it just lays out the difference. The pixel paradigm, the old way, was all about mimicking patterns to create something that looked right. The particle paradigm, the new way, is about simulating processes to create something that is right, something that's physically valid, because it's not just learning from data, it's learning from the laws of physics themselves. And to do this, you need a whole new set of tools. We're moving beyond VAEs and GANs to new architectures, like physics-informed neural networks, or PINs, and graph neural networks, GNNs. Think of PIN as an AI that has a physics textbook open for reference, making sure its answers actually obey physical laws. GNNs, on the other hand, are designed to understand relationships, which makes them perfect for simulating how individual particles or nodes in a system all interact with each other.
So what exactly is a PIN? Well, it's a neural network that's basically graded on two things. First, does its output match the real-world data we gave it? And second, does its output obey the fundamental laws of physics? This physics-based penalty acts like this powerful guide, letting the AI make really accurate predictions even when the data is noisy or incomplete. And that is a total game changer for science and engineering.
Now, this whole shift from imitation to simulation, it's not just some academic exercise. It's a genuine superpower that is already transforming how we engineer and discover things out in the real world.
And the applications are just incredible. In Hollywood, Disney used an AI simulation system called Swoop to create that photorealistic snow and water in Frozen 2. In engineering, AI is coming up with these radical new designs for parts that are stronger and lighter than anything a human would ever think of. In science, it's literally generating brand new molecules for drug discovery from scratch. And in gaming, it can build these vast, physically realistic worlds on the fly.
This quote here really points to where this whole trend is heading. Frameworks like FIA-GPT are turning AI from just a tool into an autonomous agent. An engineer can just describe a problem in plain English, and the AI handles the entire workflow, creating the 3D model, running stress simulations, analyzing the results, the whole shebang.
And this all leads to this amazing concept of the digital twin, a perfect virtual copy of a real-world system. Generative AI makes this idea even more powerful by simulating super rare events, like an engine failure, to create training data that would be impossible to get otherwise. This lets us test and optimize a system in the virtual world before we ever have to touch the real thing.
But this incredible power has a dark side. As our ability to simulate reality gets closer and closer to perfect, we have to start asking some pretty tough questions. Like, what happens when the fakes are so good they start to have real-world consequences?
Let's start with one of our most trusted institutions, science. This ability to generate physically plausible simulations creates a direct and really serious threat to research integrity.
Okay, here's part one of the thread. An AI can generate a plausible simulation of pretty much any scientific experiment you can think of. The problem? The data it spits out can look completely real, right down to the last decimal point, but be entirely fabricated.
And here is the knockout punch. That same AI can then write a fraudulent research paper based on its fake data, a paper that is so well written and so technically sound that it's been described as highly convincing even to the expert reviewers whose job it is to spot this stuff. This 1-2 punch is, well, it's pernicious. It strikes right at the heart of the scientific method.
And this threat extends way beyond the lab. A report from the Department of Homeland Security warns that for bad actors, the simulation doesn't even need to be perfect. It just needs to be convincing enough to trigger a real-world human reaction. Imagine a simulated video of a chemical spill causing real public panic and a dip in the stock market, or fake sensor data tricking a power grid into shutting down. For an attacker, the appearance of reality is the weapon.
And that leaves us with a really profound final question, doesn't it? We've gone all the way from pixels to particles, from just mimicking patterns to actually simulating processes. But when a simulation, a fake, can cause real panic, move real markets, and fool the very best experts, well, the line between what's generated and what's real just starts to dissolve. And figuring out how to navigate that new reality, that's the challenge for every single one of us.